Oh, good, green button. Hi, I'm Carl, back up here again. Network engineer over at Dyn. You know us, DNS people, internet measurement performance stuff. Okay, enough about that. So one of the things I thought would be kind of interesting, since we do DNS, we do measurements, or do anycast measurements, we should take a look at that. So, anycast, obviously the idea is you got nodes everywhere, and there's, a whole bunch around the world, and they're supposed to be, like really close to everybody. That's the whole idea of doing them. And, well, there's the whole thing of how are they connected? Do you just buy transit in all the sites? Is there peering involved? Or are they basically just dropped in, ISPs where it'll be obviously a mix thereof? So I thought, let's kind of, take a look at some of that stuff, do some measurements. So we kind of generally accept that, anycast is good, and a whole lot of anycast, that must be really good, because, it's more is better. And peering is always considered to be a good thing, so, So the kind of questions I was asking was, do more nodes make better connectivity? And, basically, is peering better than just having transit by itself? So basically all I'm measuring here is network latency. I'm not doing a Jeff Houston thing. It's just basically trace routes, how long does it take to get there. I needed some anycasts, so I thought, hey, root servers, that works. Some of them have only a few, some have a lot. That works. But I needed something that was only transit, so disclaimer, did not use Dyn's own DNS service. Instead, picked one of our competitors, and picked something else that also has some peering, for contrast. This is a lightning talk. Anyway, yes, eye chart here. Basically, the idea is we don't want to see a lot of green here. So, but this is the A route. There's only about 5 nodes, so we kind of expect that we're not necessarily going to see that much green. There's going to be a bunch of places where it's, it's just further away. And that kind of makes sense because, if you only got 5 nodes, it's kind of hard to cover the world. So what about a root server that has, a few more? So take, for example, the F root node, somewhere around 60 nodes. And, well, it looks a little bit better, but I'm still kind of seeing still a fair amount of yellow and red here. So obviously it's, 60 nodes isn't quite, it seems, enough to sort of cover everything. Well, what if I had something that was like, even more nodes? So I figured, let's take a look at the L root node. About 150 of those, that should be plenty, right? I mean, with 150, you really have to have, pretty much everybody covered. And, well, now we've got really interesting things because, I take a look at Denver. Denver has a L root node, which, may or may not be up, but let's assume it's up. Even if it's not, I mean, San Francisco and LA aren't really that far away. But Denver is actually really crappy. Why is Denver crappy? Well, it's kind of crappy because it's going all the way over to England. So it's completely avoiding everything in the US. And there's other ones I kind of looked at in this. Japan really likes to go to either Sydney, Australia, or to Washington, D.C. One thing I should say is each of these dots represents a measurement point. So it's basically going and taking a look and seeing, how far is it from each of these points to a various L root node, then draws the appropriate color for that dot. And kind of like, well, how is this possible? So I threw a little visual, because it's just too hard to put the text output of a trace route. And again, we can kind of see the whole, Denver running across the ocean. Like I say, you've got other stuff. So one of the interesting things we've got here is that when you connect to various networks, those networks may decide to carry you quite a long ways because, well, it's peering. And of course, I would want to carry across peering. I want to carry it across my own network instead of just dropping it off to transit. It's not geographically closer, it's economically closer. So this is kind of one of the interesting things here is that even with 150 nodes, you may or may not get great performance. So you kind of look at this and kind of go like peering, meh. So I thought, well, let's take a look at something that doesn't involve peering. So take a look at this one. This IP's in it's an anycast DNS service. It's not us, it's one of our competitors. They've got about 20 nodes, and they're actually not doing too bad. For 20 nodes, there's actually a whole lot of green, and it's actually not really that bad. So it's kind of, oh, clearly the answer is, just use transit, But of course, transit costs money and so on. But it's somewhat interesting that having a lot of nodes and having a lot of peering doesn't necessarily equal having a better experience for end customers. And I thought, I really should kind of contrast that with something else. So, I mean, who else but Google? And of course, Google uses a combination of peering and transit. And they actually seem to be doing a really good job of it. So they're clearly doing a lot of traffic engineering on this to manage things. As an aside, we had some of our services, we were dropping in remote nodes, and we had some interesting things about half the world decided that Toronto, Canada was really the best place to go. Singapore, no, don't go locally, let's go back to Toronto. And a lot of that was because of one of the ISPs we were in decided that peering with certain global ISPs is a good thing, and of course the global ISPs will just like to carry it across their backbone regardless of halfway around the world or halfway across the city. So in this particular case, it's kind of shows peering can not necessarily be a bad thing. So again, what this is taking from this, and yes, this is a lightning talk. I'm doing this in like 5 minutes. This is not in-depth, deep analysis. So yes, you can poke lots of holes in this. But what I'm seeing here is that just having a lot of nodes isn't necessarily better. As we kind of saw with the L route, it wasn't actually necessarily that much better than some of the other ones that had a lot less nodes. Peering, can be kind of okay. Sometimes it works out really well. But basically, as we also discovered, you have to do a whole lot of traffic engineering whack-a-mole. I wanted to use those examples. Unfortunately, we all cleaned them up, so they no longer suck, which is good for us and then makes a bad presentation then. Peering can also be really good. You just have to kind of put the time and effort into kind of playing the whack-a-mole game and going through and keep measuring, kind of seeing where traffic is and figuring out the right communities and so on. It's a very much a mileage may vary. This is something that's kind of, like I said, was sort of thrown together. Certainly it's something that we could do a much longer talk on if there would be any interest in the community on this. So that's all I have. Thank you.
One question.
Oh, does it work? Okay, good. Dimitri Kohanek, Intuix. Have you actually used any results in Dynzone network?
We have done this. I didn't want to display our own, partially because some of these probes are co-located with our own servers, and it's kind of pointless to sort of show that it's really half a millisecond across a router. So that's why I used one of our competitors, which was also a transit only.
Right, and I think you may make it a longer talk.
Pardon?
I think the longer talk would be useful.
Okay,
thanks.
Thank you.
Randy Bush. Hi, Jay. There were two reasons for massive Anycast. One was a better customer experience, but possibly the most important one was resilience to attack. And when we see the 38 mess, et cetera, I really think you should consider not putting nodes so near the next tranche of nodes, not near your customers and eyeballs, but near the sources of the attacks to soak them up where they start.
Good point.
Thank you very much. Next up, we have Danilo asking the question, where are the Anycasters? Let's kind of see a theme emerging here.
Hi, everyone. On the last year, I've been studying Anycast, and we've done a study about Anycast. Here I'm presenting you where are the Anycasters. And I am a PhD student from Telecom Paritech. And this is a work that I have done with my supervisor, Dario Rossi, and also the other people as Diana Jumblat and Jordan Auge. So, first of all, today I will introduce you our technique that we use for geolocate the Anycast instances. And the second point, it will be our results of our IPv4 Anycast census. And there will be some screenshots of our demo software that are online and you can use. And finally, our ongoing work on the application of this work to a BGP hijack detection that for the moment we have won the hackathon from Kaiden. So, before starting my PhD, I was looking some NANOG video. There was a presentation on who are the Anycasters. And actually, so after some years, finally we came up with where they are. And this is our demo that is available online, and also all the results you can browse there. So when I started, I was checking online as like which services could geolocate Anycast. And there were some commercial database, and these are the answer. We were getting some poor answers like United States. Others were getting really precise information as like latitude and longitude, but where we tried to geolocate on a map, this was the results. After we found also some distributed measurement platform, but the result was always the same. We were getting always one answer, not a list of location. So basically, what we need is just few latency measurement. Over this one, we want to just exploit some speed of light violation. And so the measurement platform, some distributed measurement platform can do this. So how does it work? We use different platforms as like Rep Atlas, Planetal, but we can use also other. We leverage some latency measurement. We convert this latency in a radius of a disk, and we try to detect some speed of light violation. The next step is try to enumerate the maximum number of circles that don't intersect each other. That is an NP-hard problem, but there is a greedy algorithm that works quite well. The output of this phase is a set of circles that don't intersect each other. And inside each disk, we try to geolocate where is the Anycast distance. And finally, we found that the most populated city is the best choice. What we do after is to shrink the radius of the latency measurement around the city that we picked, and we iterate the process. So we are able to increase the number of Anycast distances found. So basically, this is an example. It was one target, and we just leveraged from several vantage points our measurement. And what you can see is that just the 10% of disk had a radius that was smaller than 1,000 kilometers. So the performance of the software are quite good, as like we are able to enumerate and geolocate over the 75% of the Anycast distances. We are protocol agnostic, we can use for whatever target. And we use 100 times less probes than the previous work, and we are quite fast. In a few milliseconds, we can give you the answer. Next step was the census. We had really to do a lot of work to engineering everything and let it work. So we were starting from 10,000 live targets, for one target for each /24, and we were probing them from 100 vantage points using ICMP packets. What we were doing was probing them with 1,000 packets per second, and we tried to slow down our tool just because we tried to decrease the number of packet loss that we were getting, and we were able to complete one census in a few hours. After this, we ran our algorithm that in the previous version needed 100 milliseconds. That for a census, it means 1 week. So we engineered everything. At the end, we came up with a software that is able to analyze the whole census in 3 hours. And as output, finally, we have 1,000 Anycast subnet prefix. Who are they? Yeah, here is the list. What we found was Tier 1 and some ISP, other CDN that were hosting really popular web content, and we scan also all the TCP ports. So we were finding that they are serving some different services, and moreover, there were different deployments. Some of them they're using a lot of /24, some of them just one. Next step, BGP hijack detection. We are thinking to apply this technique to find speed of light violation for some BGP hijack attack, and we won't follow two different views. The first one is a reactive tool that is able to analyze the BGP feed from some platform as BGP Stream and Isolario that have been presented here, and after run some measurement on the data plane. This introduced the problem of the timescale, because BGP hijacks, they're really of short duration. So maybe while we receive this message could be too late, On the other side, we want to scan in a practical way all the /24 and understand if we're able to see something. So finally, today I show you our software and our results of the census that were quite lightweight. Everything is open source, is on the website. You can plug your measurement or you can use directly RIPE-Atlas. And all the results of the census, there is also a web interface that you can just insert an IPv4 or just a name and you can check if it's Anycast or not. And that's all for today.
Thank you. Next up, we have Jeff Osborne from ISC talking about making the root soak up more badness.
I've got 3 minutes until lunch. Somebody time me. Let's see if I can do this. This is really going to be quick. This is generally a lightning talk. I don't have slides. I have a few minutes of something I wanted to ask about, and I didn't pay Randy Bush a penny, and he totally set me up. We're trying to expand the F-root in ways that it gets out there and sucks up more of the badness. So I'm Jeff Osborne. I'm the president of IFC. We're known for developing bind and open source DHCP, but we also operate one of the 13 root servers, the F-root. Again, everybody else helped me out with this, setting this up. You already saw the F-root as deployed. There are 58 servers around the world now. And we've wondered why it wouldn't make more sense, given changes in technology and how cheap everything's getting, to go with hundreds or possibly in the low thousands. There are a total of about less than 600 root servers in the world, and the delays getting to them are something worth looking at, but Randy brings up the much more interesting point. This is Anycast. We can really stop a lot of bad attacks out where they are if we push the servers out to the edges. To get all Sesame Street on you, let me do a little 60-second bit. All internet traffic's routed to its destination by the routing infrastructure. Anycast routing lets there be more than one destination for this. So the attack traffic's going side by side unless there's a topologically closer node, and then that's basically absorbing the attack. This is a 10-minute thing. I'm trying to do it in 3 minutes because somebody's generally timing me. Anyway, the short answer is we're really looking to get tremendously more nodes out there, and it takes a little bit of routing magic. You can't just drop a root instance in your house without some magic going on. We're looking for partners who are interested, who are deployed internationally. We think it's of value for most ISPs or CCTLDs to have a root instance to sort of keep the trouble in their neighborhood rather than having time to assemble into a critical mass and harm things at the end of a longer attack vector. So I'm not sure whether we're going to use a bunch of cheap little platforms. We've thought about things like using 1,000 minnow boards. We've thought about using containers. There are different ways to do this. We're still in the wouldn't it be better to do a lot more phase, but this spring we're trying to find partners, people interested, and input from all of the smart folks in the room. Anybody time me? Did I beat 3 minutes? I hate standing between a crowd and lunch. Thank you very much for your time. If you're interested, we are, my one slide, is this going to work? Oh man, come on. f-root@isc.org, and we'd be interested in your input. Button. There it is at the bottom, f-root@isc.org. Thank you very much.
Time for one question, if anyone has a question. Okay. Oh, wait, Jared.
Hi, Jared Motch from NTT. So in the past, I'd had a number of conversations with Jim Martin, who I think runs F-root for you guys, about asking him if there were things that we could do to help facilitate with F-root. And so this seems to maybe be a direct follow-on to maybe some of those inquiries I had to him in the past. So is he still the best person to be talking to, or is there somebody else who I should be talking to over there?
If you send it to f-root@isc.org, you're in a red shirt, so I'll have an easy time finding you when I climb down from here. We'll have
Yeah,
that
it
talk.
matches my hair. All right.
There you
Thanks.
go. Thank you.
All right, thanks, Jeff.